Okay. Now, I'll be recording this, then I will send to the other ones who are not in. Right. Let's get straight to the business of the day. And let me share my screen. May you confirm you are seeing my screen?
Not yet. Yes, we can.
Yes, we can.
You are now seeing it?
Yes.
All right. My name is written on the page there. My name is James A. And my phone number, you all have it because I'm in the group, same group with you. Right.
Yes.
Okay, so let's just go through. Let me go. Let me check. Okay. Anyways, you all have the syllabus, and
Yes.
Let me not go back to the syllabus. I think you have it. All right. So our contents of this topic one is application of symbolic notations. Second topic is network theorems. And then we will go to the electric field, electromagnetic principles, transience analysis, complex waveforms, measuring instruments, reliability, transmission lines, attenuators, filters, and photovoltaic basics. Now let's start with the application of symbolic notations. I'm sure you did write notes on this, okay?
Yes, we did.
Yes, as I advised yesterday, it's good for you to write notes. You understand better than someone who just reads. You know, our IQ differs from one person to the other, but I know even if you are that intelligent, naturally, if you write, you'll be more intelligent, right?
Yes.
Yes. So now let's start with the definition of terms, even the syllabus. If you can look at the syllabus, you can actually see these are the things that you are supposed to know. So let's start with the resistance. It is denoted by capital letter R. So it is the property of a conductor that limits current. So we all know what is a resistor. I think, let me see, here. To everyone, cannot hear anything. I don't know if it is the same to everyone. No. You are hearing me, and?
Yes, we are.
Okay, some are not hearing me. I don't know why. Okay, so resistance is denoted by capital letter R, and it is a property of a conductor which limits current. So the unit of resistance is ohm, right? And 1 ohm is defined as the resistance which will have a current of 1 ampere flowing through it when 1 volt is connected across it. It's very simple definition, and Right, so R is equals to V over current. That is, R resistance is equals to voltage, capital letter V over current, capital letter I.
Aye.
Okay, so can be capital letter V like that. And then current is denoted by capital letter I. Right, so let's define a reactance. Right, a reactance. Now, we have two types of reactance. Reactances in electrical engineering technology. That is the capacitive reactance, which is denoted by X subscript C, which is the opposition of a capacitor to sinusoidal current, right? So capacitor offers some form of resistance when current flows through it. And the formula is X subscript C is equals to 1 over 2 pi FC, where F is the current, the frequency of an AC voltage in hertz, and C is the capacitance in farads. Now we have a question there. Determine the capacitive reactance of a capacitor of 10 microfarads when connected to a circuit of frequency A, 50 hertz, B, 20 kilohertz. I'm sure it's very simple. It's a simple question. You can simply plug in these values, taking much consideration to the units. Micro is to the power minus. Is to the power minus what? Micro. 10 to the power?
Minus 6.
Minus 6, right? So I'm very sure, I'm very positive. Have you seen that PDF book that I've sent?
Which ones?
I sent a PDF on WhatsApp.
Today?
Yes, today.
Yes, we did.
Yes, so that is a very good book. It's a very good book. Every question that maybe one day I might set your exam might come from that book. So take note of that. Now let's move on to inductive reactance. XL, it's X subscript L is the opposition of an inductor to sinusoidal current. Right, the unit is ohm, and the formula is X subscript L is equals to 2 pi FL, where F is the frequency and L is inductance in henries. And then another question there. We are not going through these questions because there is anything. If you try to solve them and find some difficulties, you can always come back to me, okay? Now let's move on to the term impedance. We don't want you to be speaking while I'm speaking, and may you kindly mute your microphones. All right. Now, impedance is another term that you need to define. So it is the total opposition of current, total opposition to the flow of current, including the effects of resistance and the reactance combined. So this means we have resistance, we have capacitance, we have inductance to make impedance. So it is very easy to define it in terms of resistance, in terms of capacitance, in terms of inductance, or just define it in terms of resistance and reactance. So it is given the formula Z is equals to V over I, right? Which is R plus JXL minus XC. Okay, now I'm assuming that you know what is J here. It's now
No, we don't.
You don't? Okay, it's now,
Yeah.
yes, it's now a complex expression. The R part is the real part, and J part is the imaginary part. I'm sure you did EET 1. This is EET 2, EET 2, and it? Yes, I think you did EET 1. You should know this. It's only that I cannot. All right, let me see, where can I get an annotation there? All right, let me have a red there, right? Now, so this J represents an imaginary part of the expression, and R represents the real part of the expression, of which R now is the resistance, and all the reactances are imaginary parts. Okay, well, we'll do some calculations together as we go. All right, now let's move on. Now, if you want to find the modulus of the impedance, the formula is like Z modulus Z is equals to the square root of R squared plus the difference between XL and XC squared, where XL is greater than XC, right? And if you are to find alpha, the angle between, remember when we are talking of reactances, we might have, all right, can you still remember what is, okay, someone needs to be admitted. Let me ask you something. On the x-axis and the y-axis, which side is the imaginary, which side is the real part? This is the real part. This is the imaginary part. Okay, so if you are to draw, right, the relationship between voltage and X or reactance, we define it in terms of voltage leads current by something, a certain angle, or voltage leads current by a certain angle as well. So if you are to draw there, we might have something like this, and there is an angle there, and we have a resultant vector there. Well, this is just an introduction. We will do this as we go. Now, if you are to find the angle between this Z, okay, the angle, we find first the modulus, which is Z here, and then we find the angle. Angle, we find it by tan, arctan, the difference between XL and XC over R, where XC is greater than XL. So this is our expression for finding angle. Okay. Right. Let me clear my drawings. Sorry. All right. Moving on. Now, there is another term called admittance, right? Admittance, we have admittance, we have conductance, we have susceptance. So admittance is the reciprocal of impedance. Reciprocal of impedance, right? So let's, right, we said impedance is Z, right? Which is R plus J X, okay? X, which X representing XL minus XZ. Now, if we are to say 1 over Z, we get our admittance there, okay? Are we still together?
Yes, sir.
Yes, we are.
Okay. Now, that's the admittance there. It's very simple to define. All right, so it is the reciprocal for impedance, that is current flowing in a circuit is divided by the supply voltage. The unit for admittance is Siemens like that. Now, this expression here, Y is equals to G plus or minus JB, combines everything. That is, combines admittance, conductance, and susceptance. Okay? And this Y is the symbol that represents conductance. I mean, it's admittance, sorry. Okay, let me clear. So Y is 1 over Z. Okay? Now, let's move on to conductance. Conductance is denoted by capital letter G there. Now, the real part of the admittance is called conductance, G. And then the imaginary part of admittance is susceptance and is denoted by B. So in other words, we are saying Y, this one is equals to G. We say the G is conductance plus or minus JB, where G is the conductance, B is the susceptance, and then Y is the admittance. Okay. Let's move on. So from the right now, we are talking of, let's talk of resonance. Okay, we have what we call series resonance and also called parallel resonance. All right, now let's look at the diagram that is on the screen at the moment, right? So we have a resistance, we have a resistor in the circuit, we have an inductor in the circuit, we also have a capacitor in the circuit. That is Resistor is denoted by R. Inductor is denoted by, inductance is denoted by J, XL, and capacitance is denoted by minus JXL, right? Take note of the minus. Minus capacitor is always negative when it is in the circuit. Oh, all right, you will see as we go, because the negative, why negative? It is because when we have a capacitor in the circuit, it is always offering a negative 90 degrees lagging, okay? It will always offers a negative 90 degrees lagging. That's why the negative. And also, an inductor offers a positive 90 degrees leading. Right, you will understand this as we go. Now, from the diagram above, series resonance is attained when XL is equals to XC, when inductive reactance is equals to the capacitive inductance. And at the end of the day, the two cancels out and we will only have a resistor in the circuit. That's what we call a series resonance. So in the circuit is considered to be purely resistive. In this case, XL will cancel out XC. In other words, XL will be equals to XC. Right, so an RLC series circuit is comprised of a circuit of a coil of inductance 10 millihenries and resistance of 8 ohms and a variable capacitor of C. The supply frequency is 1 kilohertz. Determine the value of capacitor for the series resonance. Okay. Now let's try to maybe. Are we still together?
Yes, sir.
All right. Now let's try to work out this one. If this situation is at resonance, which means X. Hello?
Ini ndoda kufunza ndasarira pati achiti zvonizvo kana zviri equal zvinokanzelana nditi andaunzwisisa pakuti zvonizvo umo mudhiseketi handitine plus neminus zvinokanzelana zvakadaro here kana mama muchitaura in the event yekuti zviri equal.
Zvinokanzelana kana zviri equal, zvinokanzelana kana tiri at resonance, because our condition for resonance is when XL is equals to XC. Okay?
Right.
Yes. Let's say XL is 10. It means XC is 10 as well. And now remember that okay, sorry, let me clear this. Remember that Z is what? Is R plus J XL minus XC, and it XL minus XC, which means this component XL minus XC will be equals to 0. That's the cancelling out yacho. So we will be left with only Z will be equals to R. Okay? Yes. Now let's solve this. XC is equals to XL. So 2 pi, okay. It means sorry, 1 over 2 pi FC is equals to 2 pi FL. This.
Yeah.
This, okay? Yes. Then we want to find what? The question is determine the value of the capacitor. We want to find the value of C. Okay, so C in this case, let's make C the subject of the formula there. Take what is on the right hand side, take C on the right to the right hand side and whatever in the right hand side to the left hand side. It will be what? C is equals to 1 over 2 pi squared, and it F squared L. Can you see that?
Yes.
Just making C the subject of the formula in this case. Now we are told that this will be 1, 2, it will be 4 pi squared. F, we are told F is 1 kilohertz, that is 1000 squared times our 10 millihenries, 10 times 10 to the power minus 3, right? And then if you put this in the calculator, you should get something. Do you have calculators with you there? Hmm?
Yes.
Yes. So what do we have? What do we have? 2.5. I'm getting 2.5 micro times 10 to the power minus 6. So 2.5 times 10 to the power minus 6 farads. In other words, it's 2.5 microfarads, and it? That's the value of our capacitor. Are we together? Hello?
Yes, sir.
Okay. So let's be interactive. Now, that's it. Okay. Now, another question is here. A coil having a resistance of 10 ohms and an inductance of 75 millihenries is connected in series with a 40 ohm capacitor, 40 microfarads capacitor across a 200 volts AC supply. Determine the frequency resonance occurs. Determine at what frequency resonance occurs. B, the current flowing at resonance. Okay. Okay, someone is knocking. Admit all. Okay. All right, Saka. Let's solve this one, or you will do this on your own.
No, got it.
All right, it's okay. Now, what we have is the coil inductance. L is equals to 10 ohms. And then, no, sorry. We are saying our resistance is equals to 10, and then inductance. L is 75 milli. Okay. 75. Is happening. Okay. Anyways, let's just some of these. What is given is the X resonance occurs when XC is equals to XL. All right. Let's move on. What is it that we want? We want frequency, right? We want frequency, right? So frequency. Okay. 2 pi f L is equals to 1 over 2 pi f L. Now we want to make f the subject. Let's make f the subject. So it will be f squared is equals to 1 over 4 pi 4 pi f 4 pi LC, and is it LC? That's our f squared. So if you are to find the f, it will be the square root of that. Now f will be the square root of 1 over 4 pi LC. Okay, so that's the formula there. Now we are now right. Formula is f is equals to 1 over 4 pi, the square root of 4 pi LC, right? Which is equals to. Now we are plugging in our values there. The square root of 1 over 4 pi is just 4 pi. Our L is given as times 75 times 10, which is milli, times C. Our capacitance was given as 40 times 10 to the power minus 6. If you plug in that in the calculator, so this is all under root sign. If you plug in that, so this is the 4 pi
40 times 10.
Yeah, I left squared, 4 pi squared there. Can you incorporate squared? It's 4 pi squared times 75 micro times 40 75 milli times 40 micro, and we'll get something like right. What do we have?
See.
What do we have?
I got a 91.8.
91.888, isn't it?
Yes.
Yes, it's 91.89 hertz. This is frequency, isn't it?
Yes.
Yeah, so that is correct. Now, always if the degree of accuracy is not given, you should give your answer to 3 significant figures or 2 decimal places. 3 significant figures or 2 decimal places. All right, moving on. Let's calculate the second part there. B, the current flowing. Remember, Z is equals to R plus J XL minus XC. But this component is 0 at resonance, which means Z is equals to what? R. Therefore, current flowing is V over Z. At resonance is just V, which is 200. I mean, at resonance is just R, which is Z is close to R in this case, and our R is 10. Okay. Therefore, current would what? 20 amps. Yes.
20.
Right, 20 amps. All right, now we are done with that part. We can move on. Right, there is another term called the quality factor, which needs to be defined. So quality factor is a figure of merit for a resonant device, such as the LCR circuit. Such a circuit resonates by cyclic interchange of stored energy accompanied by energy dissipated due to the resistance. So by definition, at resonance, quality factor denoted by capital letter Q is equals to 2 pi times maximum energy stored over energy loss per cycle. Since the energy loss per cycle is equal to the average power dissipated times periodic time, Q factor is equals to 2 pi times maximum energy stored over average power dissipated by periodic time, which is 2 pi over maximum times maximum energy stored over average power dissipated, which is times 1 over resonance frequency, FR. Since the periodic time T is equal to 1 over FR, thus Q is equal to 2 pi FR times maximum energy stored over average power dissipated. Maximum, or Q is equal to omega R times maximum energy stored over average power dissipated. Right, so in other words, Q is equal to reactance over resistance. Right, so all this is just something to lead you to just a moment. All right, welcome back. Right, so I was saying this, what I've said, put a circle over is just the way to derive, is just derivation of the quality, the formula for quality factor. But the actual formula that you need to know is this: Q is equal to reactance over resistance. All right, you will see as we do my calculations of these. Right, bandwidth is another term that you need to define. Bandwidth. Right. I heard someone actually, some of these diagrams are not that clear. Okay. So at resonance frequency, current is the maximum value shown as IR, and our IR is here. This is our IR there, per point up, per maximum up. Dopana IR wedu, that's where our maximum current is realized. That's where our resonance occurs. And then also shown on are the parts A. This is our A there. And this is our B there. And this is 0.707. Okay? Also can be 1/2, sorry. It's 1/√2, right? 1 divided by √2. So this is 1/√2. Where current is 0.07 of the maximum peak, maximum value of F1 and F2. So the power delivered is I squared R. At I is equals to 0.07 IR, the power is 0.07 IR squared, which is equals to 0.5 I squared R. Yes. Correct this small r is not there. This small r here is not there. All right, so half the power that occurs at frequency FR, this is our FR here, FR, all right? So half of the power that occurs at FR, the points corresponding to F1 and F2 are called half power points. So take note of this word, half power points is an examinable point. You might find a question that needs you to define what is a half power point. Right, so the distance between these 2 points, F1 minus F2, is called the bandwidth. That is from here to this, from this point to that point, that's the bandwidth. That's the bandwidth. So you can define the bandwidth in terms of this. Okay? This okay?
Yes, sir.
All right.
Yes, sir.
Okay, so let's move on. Series AC circuits, purely resistive. When we are talking of purely resistive circuits, we only have, okay, someone needs to be admitted here. Malik Kamazai. Chendegai Wema. Okay. Anyways, moving on, purely resistive circuit, it is a circuit which have a form of resistance to the flow of current in the form of only a resistor, no reactances in the circuit. So that circuit is called a purely resistive AC circuit. We can only find a resistor in the circuit. All right. Now, in a purely resistive AC circuit, the current IR and the applied voltage are in phase. So the phasor diagram may be represented on the Argand diagram as follows. That is, right. So it's like, let's say we have our x-axis there, right? So VR is along this this direction, on the x-axis direction, and also current. When the circuit is purely resistive, the current is also along that. So the phasor, the phase difference between IR and VR is 0. The phase difference is 0. So take note of that. IR is in phase with VR. All right. Okay, so let's move on. Now, purely inductive circuit, we can only have an inductor in the circuit, right? We can only have an inductor in the circuit. So we have supply voltage VL, right? And IL is flowing in the circuit because we can only have an inductance in the circuit. Now, in a purely inductive circuit, the current IL lags the applied voltage by 90 degrees or half pi radians. So in a purely resistive circuit, the opposition to the flow of alternating current is called the inductive reactance. That is XL. We talked about this. So XL is equals to V over IL, which is 2 pi FL ohms. We talked about this. Okay, so where F is the supply frequency and L is the inductance in henries. All right, now the phasor diagram. Now the phasor diagram. Right, VL and IL there. VL and IL. So what does this mean? It means that current lags, this current here, IL here, lags the voltage by 90 degrees. Okay? Kana kuti. VL is leading current by 90 degrees. You can either define in terms of the two. Current lags voltage by 90 degrees or voltage leads current by 90 degrees. This one? Right. That's that. Now, relationship between inductive reactance and frequency is that, okay? So we have XL on the y-axis and frequency on the x-axis. Now, the relationship now you can, it's easy to see from just an observation point. You can see that as frequency increases, the inductive reactance also increases. Yes. So there is a direct proportionality between XL and F and frequency, right? So as the inductive reactance increases, frequency also increases. Now, let's move on to the purely capacitive AC circuits. In a purely capacitive AC circuit, the current leads the applied voltage by 90. Okay? And we talked about this formula before, 1 over 2 pi f C for the capacitive reactance. So the phasor diagram of these is shown here on this diagram there. This one. What are we saying? We are saying current leads the voltage by 90 degrees. Okay? That's what this comes from. The negative X C there. When we have a capacitance in the circuit, which means the reactance is always negative. We will see this when we do the calculations on on network theorems? All right, so for now, don't worry much about that. So the relationship between capacitive reactance and frequency is there, shown on the diagram there. This one, right? As frequency increases, you can actually see from this relation, from this formula 2 pi f c. Now, if we have, let's say, frequency 1 hertz here, obviously the value of xc is high, and because 1 over a small denominator, we have something like bigger number, right? If we have now, let's say we have 1000 hertz, 1 over 1000. For example, 1 over 1, suppose, is just 1. What about 1 over 1000? 0.000 something, I didn't. That's why the diagram is like, the graph is like that. As the frequency increases, capacitive reactance becomes 0, almost 0, or almost very small. So this is what is explaining the relationship between capacitive reactance and frequency. Now the RL circuit, there is a situation where we have the resistor and a capacitor, an inductor in the circuit, same circuit. So this is the RL series circuit. These are in series. So the circuit containing inductance and the resistance to the applied voltage. So the applied voltage V is the phasor sum of VL and VR. Now, in each of these components in the circuit, drops have some voltage drops across it. So across R we have VR, across L we have VL. Right, from Kirchhoff's voltage law. Yes, you know that. We know. I'm assuming that we know that the phasor sum are not necessarily the phasor. No, it's not the phasor, but the sum of all the voltage drops are across or in a circuit is always 0, is equals to 0. The phasor sum of all voltage drops in a circuit is always or is equals to 0. Okay? Right. This one, leave it to the network theorems. I gave you notes on network theorems. We'll discuss about them. Right. Now, so, and this, thus the current I lags the applied voltage V by an angle lying between 0 and 90, depending on the values of VR and VL, shown as an angle alpha. In any C-series circuit, the current is common to each component, and thus it's taken as the reference phasor. From the phasor diagram, the voltage triangle is derived. So there is the phasor diagram there. On the right hand side, left hand side, on the y-axis we have VL, on the x-axis we have VR, and then the resultant voltage, which is V there, is denoted or is shown on the diagram there with an angle formed between the resultant and VR. So tan alpha is VL over VR as shown there. Right. So In an AC circuit, the ratio applied voltage V over current is called the impedance. We talked about this. We talked about impedance, right? So if, right, you can get some questions from these, from A, B, that is purely resistive, purely inductive, and purely capacitive. You can get one question or two from this. I mean, not necessarily you can get, but I'm saying these are the areas where some examination questions comes from. All right. Moving on to, right, there is this what do we call an impedance triangle. So each side of the voltage triangle is divided by the current. Then the impedance triangle is derived here. So we have R and Z there and XL there. All right. Now, we have in a series RL circuit, the PD across the resistance R is, excuse me, 12, and the PD across the inductance L is 5. Find the supply voltage and the phase diagram between current and voltage. Right. It's a question. It's a question, right? Question is saying, in a series RL circuit, the PD across R is, right, in this case, let me draw this. We have something like, we have a voltage there. I mean, we have a resistor there. We have an inductor there. And then we have a supply V supply there. So it's written VR is equals to 12 volts. And then VL is equals to 5 volts. Find the supply voltage. We want to find V supply here. So V supply is what? What do you think? Hello? What do you think is the supply voltage?
I think it's 17.
Just plain 17. No, it's not 17. Because remember, VL voltage across an inductor has some phase difference there. So if you are to write it plainly, we can simply write J5 V. Like that. Okay. Okay. VS supply is just 5, which is the not 5. Okay. So that's that. And it, because we cannot take these 5 volts across L, VL. Sorry. Is it? VL is not just 5. VL there is not just 5 because it's an inductor. It has some phase angle associated with it. So it's a what? A positive because it's an inductor. It's a positive. So it will be VS is equals to 12 volts because R is just pure resistor, which is the real part plus. Since it is an inductor, it will be plus J5V. If it was a capacitor, it was going to be 12 minus J5V. Now this positive and negative explains the negative and the positive that we discussed earlier. You will see it as we go. So that's the answer that we are looking at. 12 plus 5V, because the inductance, the voltage across the inductance, the voltage drop across across inductance is imaginary. All right. Okay, so there is another question here. A coil has a resistance of 4 ohms. Let me work out this one. A coil has a resistance of 4, inductance of 9.55 millihenries. Calculate the reactance. First things first. Z is equals to R plus. No, the question is saying calculate the reactance. Reactance. Reactance is either XL or XC or XL. And in this case, we are only concerned about the reactance of XL.
Yes.
XL, only XL. So it's what? It's like XL is equals to 2 pi FL. All right. So this will be 2 pi. F is what? 50. L is 9.55 times 10 to the power 3, right? Then you put this in the calculator, you should get an answer. Do you know, Anachi? What is it that we get? May you put this in the calculator, please?
Say, sorry. Where are we getting the 50 F?
Frequency is given panel. Yeah? Did you see it?
Yes.
Yes. Frequency is given there.
Right.
It's given at the end, of course. So you should at least read the whole question before you try to attempt.
Okay, see.
No, this should not take you time.
3.
You got 3, right?
Yes.
3.0002
0984.
ohms.
Yeah.
You remember these are ohms. Okay. Now, the second question is saying the current taken from a 240 volts. The current taken from a 240 volts. V supply is given as 240 there, volts. And we have our impedance as 4 plus J3. And remember, 3 is the inductance, is the reactance. Okay, plus 3.
Yes.
This will be in ohms. Now for you, maybe this is a bit earlier for you, but let me just go on and work out this. Okay, now for you to be able to find the current, you need to convert Z in what we call polar form. This is not new to you, is it? We need to convert Z is in triangular form to polar form. This is a bit early for you maybe because we haven't done much of this, but let me just do this for you so that when you meet something like this, you can work out something. Now, we talked about this earlier. We said if you want to find the modulus of that, it would be what? R squared plus X squared. This one? Yes. All right, let me erase this so that I create space. Right, it's Z is equals to 4 plus J3. All right, so that is the modulus Z is equals to the square root of 4 squared plus 3 squared. What do we have? Square root of 25, isn't it? So our that is
the square root of
it's root 25. So our is it R, is it Z? No, it's just modulus Z, and modulus Z is 5. Now we want to find the angle. Now we say the angle is what? Arctan X over R, and is it? So in this case is what? Our X is what? 3 over 4. What do we have?
$6.87.
What?
36.8.
36.87. And is it?
87. Yeah.
87. All right. So now we want to find current. Current is V over Z, which is equals to V is 240 over. Now we take 5 angle 36.87 degrees. This way we can calculate current because you cannot mix this form with, because this one is angle 0 there with this form. You cannot mix triangular form and polar form at the same time. Now you can now divide. You can divide there. What do we have? 240 over 5.
240 over 5 is 48.
Yeah? 240 over 5?
240 over 5 is 48.
48, and it?
Yeah.
So it's 48 angle. Now, if it is like this, we are dividing. If you are dividing the angles, you subtract. So it will be 0 minus 36. So it will be minus 36.87 degrees. So this will be your current in amps. Simple, and
Same as it's a cross and bichan.
all right, guide it over.
Yeah.
Especially by angle.
All right, it's okay. Let me find the space you can where are we? All right, I will write Pamsoro and it known. I will write Pamsoro Pema whatever is written there. All right. We said our V supply is what? 240. This is volts.
Sure.
Our V supply is at 240 volts.
But yeah,
Yes. And our R is what?
it was 5.
Is it 5?
Not so sure.
Yeah? That one. So we have question E and
R is 4.
R is 4.
Oh, yeah, it was 4.
So R is equals to 4. V supply is 240. And inductance, I calculate, I got 300. XL gave us 3. Now I said Z is equals to 4 plus J
3.
XL, which is 3.
Yeah, sure.
This is in triangular form.
Okay.
Yes, it's in triangular form. But remember now that V supply has a phase angle of 0 degrees. Always has a phase angle of 0. If it's not given, it's 0. And it?
Yeah, sure.
Yes. Now, the next thing is to convert this into polar form.
Oh, okay.
Yes,
All right.
because you cannot mix this and this if this is not in the polar form like this one. This, okay?
Yeah, sure. All right.
Yes. Okay. Now, especially when we want to divide later. Okay, now let's move on. How do we convert this into polar form? You simply find the square root of R squared plus X squared. So in this case, it's what? 4 squared plus 3.
4 squared plus 3 squared.
Yes, squared. The one here, so it's what? It's 25 because 4 squared is 16 plus 3 squared is 9, which is 25. So the square root of 25, we all know that is what? It's 5.
It's 5.
And it?
Yeah.
Now, if it is 5, now we want to find the alpha. Muri kuona kwandiri kunyora uko? Kuri kukanya?
Okay. It's okay.
Kana kuchionekwa bo. All right. Now we want to find alpha. How do we find alpha? We talked about this in brief, though we will dwell much on this when we I think we'll do some topic in some of this comprehensive stuff on this. So we said it's arctan x over R.
R.
X, so in this case, it would be XL because the lineage the inductance. So this would what? Tan inverse of 3 over 4. Now you find your tan inverse. Do you 36.87.
36.87. Yeah, sure.
Degrees, isn't it?
Yeah.
Right. Now, Yakunzi, if we are to write Z in terms of everything, now it's now in polar form. We go to at 5 angle 36 positive 36 point 0.87. This one.
0.87.
Yes, 36.87. Okay. Now we want now to find the current, because the question is saying current taken from 240. Now it's 240 angle 0 degrees over 5 angle 36.87. Now to know and achieve from this.
Yeah, that's 148.
The 148 angle. Now, if we are dividing, we subtract the angles. If we are multiplying, we add the angles.
We add the angle.
Yes. I think you will meet some of this stuff, Kumet's De Moivre's theorem. You know, the De Moivre's theorem. I think it will be clearer, but we will do this as well. This was just, it's a question that was put here for you to practice, but now we subtract 0 minus 36.87, and it? So it will be 48 angle minus 36.87 amps.
Okay.
Mm-hmm.
All right.
Yeah. So this is how we get to that. Now clear?
Yeah, I understand the idea, I think.
Okay.
No, say Kupapa Machi. Say Kupapa Machi 240 angle 0 over 5 angle 36.8. I know the not might just say after that.
Over 5. All right, let me write this big subpedaling. Tati Suzuki 240 angle 0 over 500 angle 36.87.
6.87.
Yes, is equals to, we divide this and it, you know, 48.
248.
If you were to find the angle now, you subtract triple divider 0. When we are dividing, you subtract the angles. That is 36.87. This one?
Yeah, sure.
0 minus 36.87 is minus 36.87. So this will be your final answer in amps.
Okay.
Yes. Suppose it was 240 angle 0 times 5 angle 36.87. It was supposed to be, sorry, it was supposed to be like 240 by 5.
1,200.
1.2. What is it? Angle 0 plus 36.87. It will be 1.2 angle 36.87 amps. Suppose we're multiplying. So if you are multiplying, you add the angles. Okay, if you are dividing, you subtract the angles. Clear?
Yeah, partly.
So,
Vamwe vari kuzvinzwa here? Ndiri kunzwa vanhu 2 ndonga ndo vari kuresponda.
Akawanda anonganyara.
All right. So, thank you for keeping quiet. At least we don't want noise, and yeah. It's okay. All right. Right. So what we were doing on series RL circuit, now we are on the series RC circuit. Okay, series RC circuit. Take note of this series RL where, okay, the component was not put there, but I think you have appreciated. There was supposed to be like this. This formula was supposed to be there, of showing you how to calculate your modulus Z there, and how do you calculate the angle there, right? It's okay. Now we are now dealing with capacitor. Now the method is just the same. It is just the same. The only difference is that a capacitor, when it is in the circuit, it lags the voltage by 90 degrees. But whatever, everything is just the same. Formula for calculating reactance is just the same. Right, let's just go to the question straight. The question is saying, a resistor of 25 ohms, R is equals to 25 ohms. Hey, I'm a bit right hand. R is equals to 25 ohms, right? And is connected to a C in series with a capacitor C of 45 microfarads. Then the impedance, calculate the impedance. Now, take note that question, the first one, says, was asking you to calculate the reactance, not the impedance, the reactance. Impedance and the reactance, these are two things which are different. Anyways, impedance is just either XL or XC, but this is reactance. And then impedance, which is Z, is R plus XL or XZ, XC, sorry. This okay? All right, now let's move on. Calculate the impedance. Sagatrukuda Z is equals to R was given as 25 plus what? Plus J. Oh, in this case, it's not plus. It is minus because it's a capacitor. Always, when you see a capacitor in the circuit, it offers a negative impedance. Not a negative impedance, but it lags the voltage by 90 degrees, thereby introducing the negative component there. So Z is equals to R minus J XC. So this will be 25 there minus J. Okay, first things first, we need to calculate XC. XC is 1 over 2 IF, which is equals to what? 1 over 2 pi frequency was given as 50. And is it?
50.
What do we have here?
Mm. $7.96.
7.96.
Yes.
Okay. Do I took one attested?
For me, no, 0.0031.
Yeah. We are talking about our then.
Mayashli.
Huh?
Maya.
Maya.
Yes.
Okay. Can you re-enter your values in your calculator correctly? Because it's 0.03183 and it's
Eh,
0.003.
0.003183.
183. Do you know now?
We can continue, say.
All right. Anyways, let's continue. Right, so that's our reactants there. So impedance is 25 plus, no, it's minus actually. It's minus J 0.003183. This way. Now, let's find the modulus of Z. It's 25 squared plus minus 0.003183 squared. No one anganya.
Not 25.
125. Now we want to find the angle to what? 0.003183 divided by 25. What do we get there? Faster, faster.
And 89.9927. I think it's about 90 degrees.
Almost 90, and it is
Yeah,
almost 90 degrees.
almost 90. Yeah.
Yes. Almost 90 degrees. Are we all getting something like that?
Yes.
Yeah. Okay. Right. Right. There is another question that follows there. Okay. Find also the phase angle between supply voltage. Next question in engagement current. Calculate the reactance B current taken from 240. Okay, now let's calculate the current. Current is V over G, Z, and our supply voltage is 240 angle 0 over Z. Z 13 25 angle G, angle 90.
Yes.
This one. So what do we have here?
240 divided by 25 is 9.6.
9.6. Angle
Angle negative 90.
negative 90. And that's it. That's the current there. Then find also the phase angle between the supply voltage and the current. Remember, the supply edu the 240 angle 0 and current 9.6 angle minus 90 degrees. So what do you think is the phase difference there? Wow. All right, let me ask you, if you are looking at at these two, which is leading what? Ndeipi iri kulida imwe?
Say,
Voltage is leading current.
Voltage is leading current.
Voltage is leading current, and also not something like I said always. If we have a capacitor in the circuit, it introduces a negative
90.
90.
say,
Yes.
sorry, network yangu yamboenda ndasarira patachitsvaga engo.
Patachitsvaga angle. All right. Patachitsvaga angle ndepapi zviya. Patachitsvaga angle.
But that arctan of
0.003.
Do patazowana arctan, I mean tawana 90 degrees. Tawana 90 degrees.
All right.
Yes. Saka 90 degrees here, do bataibatanidza nechi need this 25, which is our impedance. The modulus. So it's 25 angle 90. And then we divide that to get 9.6 angle minus 90, because it will be 0 minus 90. Now, the question is saying, find the phase angle between the supply voltage and current. Now, you look at these two, voltage and current, which is this one. You can observe that the angle voltage is like, let's draw this. Sorry. Let's draw this. This is V supply. It is along because there is no phase. The phase angle is 0 here, and then positive, negative 90 is what? So current I supply is this one, minus 90. This one?
Yeah. Yes.
So current, because we always move in the clockwise direction. No, yes, we move in the clockwise direction. That is in this direction, in the anti, sorry,
Anti-clockwise.
in the anti-clockwise, so like this. So if, suppose current is here, and voltage is here, which means voltage is leading current by 90 degrees, or current lags voltage by 90 degrees, depends with this lead and lag. So use these two, you can use these two interchangeably, but now you should know which component are you putting first, either current or voltage. Yeah. Okay. Right, the following, I mean, the next question, Papa, this one, Moita Megandi. Yes, amai kana maita matambudziko. Maita dambudziko tinongozoona kuti ite sei. Now, let's look at the other else. Where do we? Yeah. Well, we should at least now. I think we should do this maybe next lecture.
Sure.
Maneta.
Chabo.
Manje mukabho seni kwakadai. All right.
Dzatoma one.
Yeah, dzatoma one. Apana inini na 2 ndine rimwe lecture futi rakangoita sairori.
Asauda kuti muzoro. Yeah.
Anyways, ticha continue from F there, shenderera mberi, but zvinodipa here. Are you getting it? Right, let's unmute our mic, everyone. Okay, so let me stop sharing and stop